When we talk about things being hot and cool, what we are actually talking about is the way we perceive the amount of heat within a substance. For example, the temperature in the coldest place on Earth, which is a village in Siberia, can reach negative 70 degrees Celsius. So for a person who is used to living in that place, and believe me, there are people who live there all year round, a temperature of 0 degrees might feel pretty warm. On the other hand, for someone who is living in the southern state of Kerala, a temperature of 10 degrees may feel too cold. So clearly, our perception is very imperfect at deciding what is hot and what is cool. So what is the scientific basis for deciding this? How do we categorize things for being hot or for being cool? The answer lies in a concept called equilibrium. Now, you're already familiar with equilibrium in a different sense. Let's take an example. Let's say that we have an inclined plane made out of wood, and on this plane we have a block made out of cardboard. Now, there will be some frictional force which is acting on the block and on that inclined plane. And this friction is preventing the block from moving. If you were to actually look at the forces acting on this block, you would notice that all the forces are adding up to 0. So we say that there is no net force acting on this block. If we were to take the same block and put it inside free space, far away from any planets or satellites or galaxies, it would simply remain there. Because of its inertia, it would not move, it would just remain stationary. Are the two conditions equivalent? Yes, the forces acting on the block are 0 in both cases, but we clearly see that these two situations are not the same. So this will give us some idea of what we actually mean by equilibrium in physics, and how this understanding of equilibrium allows us to define something else of great importance in the study of thermodynamics. The concept we are going to understand, equilibrium, can be thought of in the following way. A system is said to be in equilibrium if its properties do not change with time. Let's consider a simple container which contains some kind of gas. Now, there are various properties we can associate with this container. The gas is occupying some physical space, so it has a volume. It is exerting some kind of a pressure on the inner walls of this container, so it has a pressure. There are other variables as well, like enthalpy and entropy, that we will not go into now. But we understand that this gas placed in this container has a set of properties and can be defined by those properties. We say that this system, that is the container with the gas inside it, is in equilibrium if these variables like pressure and volume do not change with time. So if the pressure and volume of this gas remains the same over a long period of time, for that amount of time, the system is in equilibrium. We can also consider what happens when energy is allowed to enter or exit from this container. If heat energy is leaving the container, the gas will cool down, the volume will decrease. If heat is being added to this container, if we put it over a fire, the amount of volume does not change much because the gas cannot escape the container. However, the pressure is increasing. But in both cases, we notice that one or more variables associated with this mass of gas is changing and the system is no longer in equilibrium. Let's consider a more involved example. Let's say that we have a container. So here we have a container which is perfectly adiabatic. Now, what is this word, adiabatic? Adiabatic means that this container is perfectly insulating. It does not allow any flow of matter or heat energy from the outside in or to the inside out. So it is perfectly insulating. Now, let's say that we have a partition inside this container. So here is our partition, and we have two different gases placed inside it. So here is one gas and here is another. Now, these two gases can be characterized by various properties. So, for example, let's say that this is gas A, and here we have gas B. Gas A has a pressure, let's call it PA, and it is occupying some volume, let us call it VA. On the other hand, gas B also has a pressure, let's call it PB, and it has a volume, let that be VB. The partition between them, which is preventing these gases from physically mixing, can be of two types. If it is an adiabatic partition, it means that no heat energy or matter can travel from one gas to the other. They are completely isolated from each other. So in that case, even though PA, VA, PB and VB may be different, they can have a wide range of values. These values will not change. The volume and the pressure of gas A will remain the same. The volume and pressure of gas B will also remain the same. There will be no change in them, which means that both of these gases are in equilibrium. On the other hand, let us say that I were to replace this adiabatic wall. So I'm replacing this adiabatic wall with a new type of wall, which I call a diathermic wall. Now, what is a diathermic wall? So now, instead of having an adiabatic wall, I have a diathermic wall. A diathermic wall is perfectly conducting. It has a very high conductance to heat, so it is a perfectly conducting partition, which freely allows heat energy to move. In this case, the pressure and volumes of the gases will start to change spontaneously because heat energy is being transferred from one gas to the other. And this transfer of heat will take place until both of them reach a point where their pressures and volumes stop changing further. Please note, the pressure and volumes of these gases don't have to become equal to each other, but there will come a point where the pressures and volumes are no longer changing with time. So now these two gases have reached equilibrium. So is there some property that has to become the same for these gases for them to get into equilibrium? We just said that two different gases can be at different pressures and volumes and still be in equilibrium. So is there something that is same between them? To learn how this property has been found out or how we defined this property, let's think of a slightly more detailed experiment. Let's say we have a more complicated box. So here is a box, and in this box there is a partition. And this partition is perfectly adiabatic. So here we have a perfectly insulating adiabatic partition. Now, there are two gases on either side. So we have gas A and we have gas B. And they cannot directly communicate with each other, or in a different sense, they cannot really transfer any heat energy directly to each other. On the upper side, we have another partition. So here is a second partition. And unlike the first partition, this one is perfectly diathermic. So this here is a diathermic partition, which means it is perfectly conducting. And there is actually a third gas here. So we have gas C, and all of these gases have various pressures and volumes when we begin the experiment. So we have PA, VA, we have PB, VB, and we have PC, VC. Now remember, gas A and gas B cannot directly transfer any energy. However, they are perfectly capable of transferring energy with gas C. What do you think will happen over time? Over time, we notice that even though A and B are not directly in contact, they cannot transfer any heat energy. If we were to reverse the order of these partitions, for example, if after a long period of time, I were to make this partition perfectly diathermic. So I'm changing this adiabatic partition to a diathermic partition. And if I were to change the previously diathermic partition to an adiabatic partition, I would still notice that gas A and gas B have reached thermal equilibrium. They are no longer changing their states. Their pressures and volumes have reached a point where they are exchanging energy. They have stopped exchanging energy and now they are constant. Also, they are no longer exchanging any energy with gas C, even though gas A and gas B were not in direct contact with each other and could not directly exchange energy with each other. This experiment gives us the basis for the concept of thermal equilibrium in terms of the zeroth law of thermodynamics. It is called the zeroth law because it was devised by a scientist named Fowler after the first and second laws had already been named and numbered. What does the zeroth law say? Zeroth law says that if two systems, let us say we have two systems A and B, are in equilibrium with a third system, C, they will also be in equilibrium with each other. So coming back to the question, is there a property that all these three systems share because of which we can say they are in equilibrium? And if you guess that that property is temperature, you are absolutely correct. Systems come into equilibrium when their temperatures become the same. So their pressures and volumes keep changing until the temperatures for both of these gases or both of these systems become equal. Once the temperature becomes equal, there is no net flow of energy anywhere inside the system. And that is what we call the zeroth law. The zeroth law also gives us the basis for thermometry because it allows us to come up with a definition for what temperature is. That quantity which is same for two systems which are in thermal equilibrium with each other.
Manorama Horizon. Learning made simple.